All right, so I have 4 pages of notes I would like to get through today. We'll see if that happens. And the first thing that we're going to talk about is semiconductor basics. So hopefully you all remember this. Semiconductors are a group of materials whose electrical conductivity lies between that of conductors like copper and silver and insulators like glass and quartz. There are 2 fundamental types of semiconductors. There are single element semiconductors. So if we look at that periodic table over there to you guys' left, group 4, which you can't actually see, so column 14 is where most of these single element semiconductors lie. So silicon is the most common semiconductor that's used. Before silicon became a big deal, it was germanium, widely used as a semiconductor still in a lot of applications. And much more recently, specific carbon allotropes like carbon nanotubes and graphene have been entering the semiconductor space as well. So everything in element 14 there usually winds up getting used as a semiconductor, but specifically carbon, silicon, and germanium, those top 3 are what are in the most wide usage. In addition to single element semiconductors, we also have multiple element semiconductors or compound semiconductors. So silicon carbide, we put 2 elements from group 4 together, we still get a semiconductor. Silicon germanium is also a semiconductor. We can also take elements from group, group 4 and group 6. Sorry, hold on. No, group 3 and group 5, sorry, because it doesn't say the groups on there, I'm getting confused. So like gallium arsenide is a very widely used semiconductor. Gallium nitride was used a lot at the Air Force Research Labs when I was up there back in 2015. There are also, those are examples of like binary semiconductors because they're composed of 2 elements. There are also tertiary semiconductors comprised of 3 elements and all kinds of stuff. I'm not going to go into all of them because limited uses and all that kind of good stuff. So just know that semiconductors are all kind of floating around between column 13 and column 15 for what we are concerned with. All right. Okay, so time to write crap down. Most semiconductors are crystalline in nature, okay? Like silicon, which is what we're going to spend the overwhelming majority of our time talking about, has a diamond crystal structure, which, did you guys learn about crystal structures at all in 334? Okay, so a diamond crystal structure is a face-centered cubic lattice with a 2 silicon atom basis, or another way to think about it is an FCC tucked inside another FCC. If we looked at one crystal plane, we might see something that looks like this. So all of these circles here are representative of the silicon nuclei. Silicon has 4 valence electrons, which means the nuclei should have a charge of +4. And silicon crystal is formed when a silicon atom covalently bonds with 4 of its nearest neighbors. So I'm going to represent these covalent bonds like so, where each of these lines represents a single electron. This is a covalent bond, meaning that the electron is shared between those two silicon atoms. All right. So at a temperature of 0 degrees Kelvin, or absolute zero, our crystalline structure should be extraordinarily nice and uniform. And it's going to give rise to what's called an energy band structure. Do you guys talk about energy band structures at all in 334? Great. So our energy band structure should look something like this. So this is going to be our conduction band, and it will be empty at 0 degrees Kelvin. And then down here will be our valence band, which will be full at 0 degrees Kelvin. Down here, our energy is 0. This is EV, the energy at the edge of the valence band. This guy is EC, the energy at the edge of the conduction band. This top bit here is EC plus our electron affinity. So that tells us how much energy it requires to literally rip an electron away from a silicon atom entirely. And then this range between EV and EC is our band gap, right? So in a semiconductor material, we have a region of energy values between EV and EC that is completely devoid of energy states, right? So there's nowhere for electrons to go. They have to, they want to be at a low energy state, so they're all hanging out here in these literally billions and billions of discrete energy states that make up the valence band until they get enough energy to jump across this gap, leaving an electron available for conduction, so a free electron in the conduction band, and a hole available for conduction in the valence band, right? For silicon, the band gap is 1.12 electron volts. Don't expect you guys to remember that. I'll give it to you in tables and all that crap for all your problems and everything. So at T is equal to 0 Kelvin, silicon is an insulator, right? Any material where the valence band and conduction bands don't overlap will be an insulator at 0 degrees Kelvin, because there's no energy in the system to make electrons jump from the valence band up to the conduction band, right? So as temperature increases, what starts to happen? Anybody got any thoughts? What starts to happen to the crystal structure?
Starts to break down a little bit.
Starts to vibrate would be how I like to think about it, right? So imagine that all of these covalent bonds are springs. When they're not completely frozen, there starts to be a little bit of wiggle room due to heat energy in the system, right? And so what would happen is that, let's say that this atom moved to the left and this atom moved to the right, so that that spring gets stretched so much that it breaks. Well, when that bond breaks, right, because the forces between the atoms, you guys haven't had fields yet, are very, very dependent on the distance between the particles and all that kind of stuff. So when they get too far away from each other, you'll see that their interactions are much, much weaker. And what will happen is a bond will break, and the breaking of that bond will result in an electron and a hole being formed, right? So we now have two free charge carriers effectively. So we're going to wind up with a hole in the valence band and an electron up here in the conduction band, and it will fall and sit in the lowest possible energy state after a little bit of time, okay? As the temperature, before we talk about that. So this process of creating electron hole pairs is called thermal generation. Excuse me. So as our temperature increases, we're going to see more and more bonds break because there's more and more thermal energy in the system. So we might have another electron hole pair get generated, and maybe another one over here as well. All right. So as temperature goes up, the probability that an electron hole pair will be generated also goes up, right? So this concept of thermal generation is extraordinarily temperature dependent, which makes sense because it's got thermal in the name, right? When a wandering electron in the conduction band meets a hole in the valence band, recombination occurs. And so what happens is that electron hole pair gets annihilated because the electron is no longer up here in the conduction band available for conduction. It's down here filling up an empty place in the valence band. The rate at which recombination occurs is dependent on the number of electron hole pairs that have been generated. And the number of electron hole pairs that have been generated is highly dependent on temperature, which we've already talked about, right? So at thermal equilibrium is the point at which, in the system, at which the rate of new electron hole pairs being generated is exactly canceled out by the rate of recombination. So at thermal equilibrium, there will still be electron hole pairs, but the number isn't increasing or decreasing. It's at an effectively constant value, okay? So at thermal equilibrium, the free electron concentration N that is not how you spell free. Is equal to the whole concentration P, and both of these guys are equal to what's called the intrinsic carrier concentration, which is Ni. N, P, and Ni are typically measured in units of per centimeters cubed. So what is the intrinsic carrier concentration of silicon at 300K? Anybody? I'm sure you guys talked about this in 334. Well, what did you say? 1.5 times 10 to the 10 is a common value. 1.0 times 10 to the 10 is a common value. 2.0 times 10 to the 10 is a common value. These are all statistical things based on Boltzmann statistics, their probabilities. And the value is not something that's set in stone, okay? Different pieces of literature refer to it as kind of significantly different values, but it's usually going to lie somewhere between 1 to 2 times 10 to the 10 atoms per centimeter cubed. So mathematically, the intrinsic carrier concentration Ni is equal to B times T to the 3/2 multiplied by the exponential function acting on negative Eg, which is the band gap, divided by twice kBT. Oh my goodness, my mustache is driving me insane. All right, so a couple of things here. Kb is the Boltzmann's constant. 1.3065 times 10 to the negative 23 joules per Kelvin, or 8.61733 times 10 to the minus 5 electron volts per Kelvin. You guys all know what an electron volt is, right? Literally the charge of one electron multiplied by 1 volt. So 1.60 blah, blah, blah times 10 to the negative 19 joules. This guy B right here, in my opinion, is interesting. Okay? This isn't something that you need to particularly write down, but the textbook that I have chosen for this class says that B is a material dependent constant. That's literally all that it mentions. That's not wrong, but it's an overwhelmingly simplified view of what that coefficient is. From your solid, so does this equation look vaguely familiar from your solid state class? So B here is representing the square root of the effective density of states in the valence band multiplied by the square root of the effective density of states in the conduction band. Both of those quantities are proportional to effective mass and temperature. And then both of those proportionalities are actually to the 3/2 power. And so what that means is that the intrinsic carrier concentration, while it looks like it's only dependent on, I guess, the square root of temperature cubed, it's actually dependent on temperature cubed entirely, right? T to the 3rd power, okay? Highly, highly, highly temperature dependent, okay? So I just want to point that out because a lot of things that I've seen will say, oh, temperature, the intrinsic carrier concentration of silicon is, 1.5 times 10 to the 10 atoms per cubic centimeter at 300 K. And then they use that exact same value at, say, 375 K. And that number is wildly not correct, okay? There is a huge, huge temperature dependence here that we absolutely need to take into account. So we need to get into the habit of being able to quickly calculate what the intrinsic carrier concentration should be for any given temperature. That's going to be one of your first homework assignments. All right. So this is intrinsic semiconductors in a very, very condensed form. Anything out of the ordinary or not agreeing with what you learned in 334. All right. So let's take a few minutes and now talk about extrinsic or doped semiconductors. All right, so at a normal operating temperature, somewhere close to room temperature, most semiconductor materials do not have enough free charge carriers to actually be considered a good conductor, right? So conductivity is given by Q, the elementary charge, times N mu N plus P mu P. So let's unpack this guy real quick. Q is the elementary charge. Has a value of 1.60218 times 10 to the negative 19 coulombs. Mu N and mu P are what are called our carrier mobilities. We're going to talk about that concept significantly on Friday. These guys are measured in centimeters squared per volt second. These carrier mobilities kind of represent how easy an electron for mu N and a hole mu P can move about in a crystalline structure. They are temperature dependent and dopant dependent, which we're going to talk about dopants in a minute, right? So for intrinsic silicon, you don't have to write this down or anything. This guy is on the ballpark of 1500. At T is equal to 300 Kelvin. This guy is somewhere around 1500. This guy is somewhere around 500. Okay. As we dope our crystals, this guy is going to go down pretty significantly. This guy is going to go down by a little bit. So it would seem intuitively like putting more free electrons into the system by doping it would make the mobility go up. It goes down because it has more crap to run into, right? So anyway, we'll talk about all that in a bit. But if we were to calculate the conductivity of intrinsic silicon at a temperature of 300 degrees Kelvin, room temperature, we'd find that its conductivity is about 3 times 10 to the negative 6 per ohm per centimeter. Ballpark a million times smaller than what a reasonable conductor would be. So a reasonable conductor would have a conductivity of somewhere around 1. A good conductor, like copper, has a conductivity of somewhere around 10 to the positive 6 per ohm per centimeter, right? So this guy is a million times smaller than it needs to be reasonable. And let's see, what's a million? Quadrillion times smaller than what it needs to be good. So to get around those very, very low values of conductivities, we put dopants into our crystal, right? To give it extra charge carriers. Since this guy is very dependent on the amount of free electrons and the amount of holes. So if we dope with group 3 elements, like boron, gallium, or aluminum, we are introducing acceptor impurities. Okay. These group 3 elements, again, boron, aluminum, gallium, have 3 valence electrons. Okay. And they create excess holes beyond Ni, our intrinsic carrier concentration, yielding p-type material. So let me leave that up on when you finish writing that down or whatever. I'm going to draw an energy band diagram, okay, to kind of explain what's happening. Because it may not be intuitively obvious why putting in an atom with 3 valence electrons winds up giving us holes. Okay, and the reason why I say it's not necessarily intuitively obvious is because our crystal, even if we dope it, is still electrically neutral, right? All of our silicon atoms have just as many electrons as they do protons. Same for all our dopant atoms. So if we put in a bunch of electrically neutral stuff into this big mix, why do we all of a sudden start having positively charged free charge carriers moving about and doing things? Okay. So I draw an energy band diagram for intrinsic silicon. Let's start there. Okay. So this guy is still my valence band. This guy is still my conduction band. We have 0, EV, EC, EC plus chi. Here's my band gap, EG. All right. So this is what it looks like when we have intrinsic concentration levels. And if we're not at T is equal to 0 Kelvin, it's very likely that we'll have some holes in our valence band and some free electrons in our conduction band, right? When we introduce acceptor impurities, these acceptor atoms have what's called an ionization energy. The ionization energy for these acceptor atoms is somewhere around 0.05 electron volts. And so what that does is it creates an energy state here, which I'm going to call EA. It's a little bit above the edge of the valence band, right? So this distance is somewhere around 0.05 electron volts. So let's say that this red, oops, that's not what I wanted to do. Thing right here represents one of our acceptor atoms, right? Kind of jumping ahead here. Did you guys talk about what a typical doping concentration was? Or did you work enough problems to kind of figure out, like, ballpark, how heavily is silicon usually doped?
Anywhere from 10 to the 15 to 10 to the 18.
Exactly right, 10 to the 15 to 10 to the 18. Silicon has 5 times 10 to the 22 atoms in a cubic centimeter of the crystal. So it might seem like 10 to the 15 to 10 to the 18 is a whole hell of a lot of dopants, but that's really only like 20 parts per, parts per million to parts per billion doping concentrations, right? It's actually very, very small. The silicon is going to behave almost exactly like bulk silicon, even when we put in a billion impurities per cubic centimeter. So anyway, we're going to have a couple of these sites that only have 3 valence electrons. So they're looking to bond. They're looking to covalently bond with other things, like the surrounding, several of the surrounding silicon atoms. And so what we might see occur is that an electron can very easily make that 1/20th of an electron volt jump into one of those waiting sites on the acceptor atom, right? And every one of those guys that effectively gets trapped up here because it takes so little energy to push it there leaves behind a hole available for our system to actually conduct well. Okay. This distance of approximately 0.05 electron volts is dependent on the dopant material, all right? So for instance, boron has an ionization energy of 0.045 electron volts, whereas gallium has an ionization energy of 0.07 electron volts, right? So it's not exactly at 0.05, but it's still going to be very, very close to the edge of the valence band. So that it's going to be very, very easy to push those electrons in the valence band of the silicon into those spots to get trapped and leave behind holes. Right? So that's where we get excess holes due to acceptor atoms. They accept an electron from the valence band and leave behind a hole. We can do the opposite thing by doping with group 5 elements, right? Oh, actually, hold on, before we talk about this. So sorry that I forgot to do this. If Na, which is the number or the concentration of acceptor atoms, is significantly greater than Ni, then the whole concentration in our p-type material, will be approximately equal to Na, and our electron concentration, Np, will be approximately equal to Ni squared over Na. This relationship is from what's called the mass action law, which I'm sure that you guys talked about but I'm just going to write it down for the sake of argument. The mass action law states that N, the electron concentration, times P, the whole concentration, has to equal Ni squared. This law is true for all semiconductor materials, regardless of whether they are intrinsic semiconductors or extrinsic semiconductors. Okay. All right. So back to effectively N-type crystals. If we dope with group 5 elements, like phosphorus, arsenic, and antimony, I believe. These are called donor dopants with 5 valence electrons. We create excess electrons in the conduction band beyond our intrinsic carrier concentration, resulting in N-type material. So we could draw an energy band diagram for this guy, and it's going to look extraordinarily similar, right? So if we start with an intrinsic crystal, band gap, we're at a temperature greater than 100 degrees, 0 Kelvin. Probably have holes available, or intrinsic holes available in the valence band and free electrons available in the conduction band. When we put in a donor impurity, we wind up generating another energy level in our band gap, okay? And that energy level is going to be slightly below the edge of the conduction band. So let's call this guy ED. And we will have sites representing our impurities. And the distance here is somewhere around 0.04 electron volts. So these impurities here have 5 valence electrons, and the surrounding silicon have 4. So it only takes about 1/25 of an electron volt to cause that extra electron to jump up into the conduction band and make everything behave like purely crystalline silicon with excess electrons, right? So these guys jump up here Oops. That looks like garbage. And that's how these donor atoms wind up contributing excess electrons into the conduction band. All right. So for an N-type crystal, if Nd is much greater than Ni, then our electron concentration is approximately Nd, and our hole concentration is approximately Ni squared over Nd. All right, that's enough out of me for today. Time's this class supposed to end? 1:45? Okay. For syllabus day. Getting out 15 minutes early. Yes, ma'am. That's a great question. And the short answer is it mostly doesn't. Okay. So what I mean by that is, even like I talked about earlier, even if we dope at the higher end, like 10 to the 18 dopant atoms, that means that we're at, so 10 to the 18 divided by 5 times 10 to the 22 is what? Like 0.00002, I think, or something like that. Okay. So we're talking about 20 impurities for every million silicon atoms or thereabouts. So it's still largely going to behave like bulk silicon from a crystalline standpoint. Now, the question becomes, are these dopant atoms interstitially added, or are they replacing a lattice site for a silicon atom? Because there is a difference, but we can't ever know which is actually happening. It's always going to be some combination thereof. The key here is understanding that while it seems like we're doping the hell out of this thing because we're putting in 10 to the 15, so that's like a quintillion dopants, compared to the actual number of silicon atoms in that same space, it's really not enough to do anything to change the crystal structure. Is that reasonable? Okay. All right, any other questions? Yes, sir. So I think the first homework is going to be posted on Friday because it'll cover this and what we're going to talk about on Friday, which is carrier transport in semiconductors. So I have 2 problems written for this, and yeah, it'll be posted on Friday and then due probably next Friday, I think. Something like that. Anything else? All right, you guys have a good next couple of days. See you on Friday.